Hey everybody, Mrs. Lowe here. This is Algebra 2, Chapter 3.3, Solving Systems of Linear Inequalities. You guys should be following along with your note guide and completing that. Save the team challenge for next class. So we're going to get right into the lesson. This will be the first video of 2. So today you guys are going to be able to solve systems of linear inequalities. First of all, a system of linear inequalities is a set of 2 or more inequalities with the same variables. The solution is often an infinite set of points. When graphed, it is the region where the shading overlaps. It's any point that satisfies all the linear systems or linear inequalities, and that's the solution. So we're going to graph each one of these linear inequalities, and we're going to see where their shading overlaps. So the first thing I'm going to do with this one is I'm going to solve for y, and you're going to notice that I'm going to divide by a -3, which is going to flip the inequality symbol. So the shading is going to be above. Now I'm going to graph that line. The y-intercept is 6. And then the slope is, oh, I made a mistake there. Do you guys see that mistake? That should be -2. I didn't divide 6 by -3, so that would be -2. So you guys got to keep an eye out for any mistakes that I might make. So the y-intercept is -2, and then you go up 1 over 3, up 1 over 3, etc. Or you could go down 1 over 3, as long as your slope is positive. The line is going to be solid because it's greater than or equal to. So a solid line, make sure you put arrows on the end of it, and the shading is above. So any point in this area is a solution to the red inequality. But this is a system. So we're looking for points that satisfy all of the inequalities. So now I'm going to graph the blue one, but first thing I'm going to do is solve that for y, just to make sure that the inequality doesn't flip over. So move the 3x over, it's -3x plus 8. So the y-intercept is 8, and it's down 3 over 1 for the slope. And I continue that across the page, down 3 over 1. This is going to be a dashed line because it's simply greater than, not greater than or equal to. And then the shading is greater, so that's above, which would be in this area here. Now, any point in the blue region is a solution to the blue inequality. But what's a solution to the system? Well, any point in the shaded region where the shading overlaps is a solution. So anything across that, along that red line and next to this blue line and in this region is a solution. So we're going to do a test point to make sure we've graphed the correct area. Pick any point you want in this area. It could be on the red line. It should not be on that blue line, but I'm just going to pick this point. 4, 0 is going to be my test point. If you shaded the right area, then the test point should work in both inequalities. So I'm putting 4, 0 into the first inequality, and I'm just seeing if that is true. It is. And then I'm going to put 4, 0 into the second inequality, and I'm going to see if that is true. It is. So I've shaded the correct area. So there is a solution to a system of inequalities. The actual shading region shows it is the solution. All the points in this area is solution. You don't have to list points because there's infinite number of them. So you're going to try number 2 on your own, and then we're going to connect this later on with solving linear programming problems. And what we would have to do for that is figure out where do those lines intersect. So the question is, where do these 2 lines, the blue and the red line, intersect? And that's what it's asking in this problem. Where do the boundary lines intersect? And is this point of intersection a solution? So I've rewritten the red one. I've just wrote the equation because the boundary line is simply the line. And then I rewrote the equation for the second one, but I brought the 3x over. So these are equivalent without the inequalities, just the equal signs, because I'm figuring out where the 2 lines intersect. So I'm going to take the blue, and I'm going to substitute it in for the y of the red. And you guys, we did this previous section. So I took the 8 minus 3x, I know that's what y equals to, and I put it right in here. And now I've just got an equation in terms of x. So I'm going to distribute. and then I'm going to solve for x. I do stay or go, so I get x, 10x equals 30, so x would be 3. Remember, that's just the x coordinate. I plug that back in to either inequality or equation, and I get my y value. I'm just going to put it in for the second one. So I get 8 minus 9, so y is -1. So the point of intersection is 3, -1. So if I go back to that line, those two lines, they intersect right here at 3, -1. That'll be important for linear programming. The question is that a solution? Well, it's a solution for the red one for sure because it's on the red line and that red line is solid. But it's not a solution for the blue one because even though it's on the blue line, it's not part of the solution because it's anything bigger but not equal to. So no, it's not a solution because it doesn't satisfy both. So not a solution. We're going to stop there, and then the next video will be on applications of systems of linear equalities. You guys can pull up Desmos while you're waiting and prepare that, and we'll get right to it. So second video coming up.